So in this video, we'll look at the topic of differentiation, and it is the most important topic in the calculus course, especially the beginning part of the calculus one. And in the previous videos, we have described it already that there's something called the limit definition of derivative. The mathematical notation is stated here, which we call f prime of x. And it is defined by a limit of h goes to 0 of a big fraction, which actually looks a little bit complicated. It is actually quite complicated in terms of computation, depending on the f you have, obviously. But usually, we would like to have some shortcut to make our calculation easier, to make our computation faster. So obviously, we don't want to spend like maybe 15 minutes to find the f prime of x just by resolving what we have in the limit quotient, right? And now, in this class is a pure computational class that you will learn quite a lot of differentiation rules. And by using those rules in a good way, in an appropriate way, you don't have to care about the limit definition anymore. That's the key point, and it makes your calculation a lot faster. But I would like to emphasize, all the rules that I will state in this video and a couple of next videos are actually derived by using this limit definition of derivative. So the origin is always coming from the limit definition, but it's just a matter of fact to speed up our computation. It's much better that you memorize a couple of rules instead of going back to the limit definition every time. That's how the differentiation rules come up. So now let's look at the first rule I stated here. If a function is a constant function, the constant is any number, any fixed value is fine. So let's say f of x is a constant. Then I claim that f prime x is 0. Do you know why this rule makes sense? I can really add a hint here. I mean, if you think about that, if you have a graph of y equals a constant, so for example, you have a graph and y equals constant is basically an horizontal line, right? I mean, it's really a horizontal line. Horizontal line. And the fact is that for any horizontal line, the slope is always 0, always. And in a previous video, I've explained it already. Slope 0 for a line essentially means that the f prime of x is always 0. And that's the reason why we have this rule that whenever f of x is constant, f prime of x is 0 all the time, all the time. So we'll go to the next rule. So let's look at the next rule I stated here. This one is called a power rule. Power rule in the sense that you actually now have a function f of x which is equal to x to the power n. N is a fixed value as long as it is not 0, it's fine. So we have the rule that in that case f prime of x is always the same as n times x to the power n minus 1. This is a quite a useful rule also. And next, let's go to the next rule. So the next rule number 3 is that we can do differentiation term by term, in the sense that if you have two different functions added up together or the subtraction of two functions, what you need to do if you want to find the derivative of that, you can just do it term by term and just keep the sign unchanged, like what I've stated here. And let's go to the next rule. So please look at the rule number 4. F of x equals k times g of x, and k is a constant here. K is a constant. So in that case, when you try to do differentiation in that case, f prime of x is going to be the same as k times g prime of x. It means that whenever you have a constant attached to a function which you know how to find the derivative of, you just need to keep the constant there. You don't have to do anything on the constant, just keep it there. You just need to differentiate the function which is attached to the constant. And these are the basic rules we have, and we'll do some exercises now. So let's look at the current exercise. If f of x equals x to the power 4, what is the derivative f prime of x? So please recall the power rule that I stated in the previous page. there was a rule like this. If f is x to the power n, f prime is gonna be n times x to the power n minus 1. And in this case, I think it's so obvious. N is just 4 as a fixed number, and f prime of x is gonna be 4 times x to the power 3, right? So the key fact is that the power is always decreased by 1 whenever you do a differentiation one time. And let's look at the next problem. Please look at the current problem now. If f prime of x as a function is gonna be 3x squared plus 6, let's find the derivative together. Now, please keep it in mind that it's an addition of two functions, right, for the f of x. So we can just do the term-by-term differentiation. It means that, for example, the plus 6 term, 6 is a constant. And we have noticed that if you have a constant, f prime is always 0. So it means the second term is always 0. And what is the first term? Let's take a look at that. First term is what? 3, you see, 3 is a constant attached to a function x squared. So 3 is unchanged. We just have to apply the power rule to the function x squared to find the derivative. And the derivative of x squared is going to be 2. You have to pull the power out, basically. You pull the power out times x to the power. And the power now is 1. Is decreased, is decreased by 1 from the power 2 here, you see? So it means it's 3 times 2x. And of course, you can write it in a simplified way. So basically, f prime of x in that case is just 6x, right? Let's go to the next problem. Please look at the current problem. Please let me know the derivative of f prime. Let's do it term by term, as I said. You see, first term, by the power rule, it's gonna be pull the power 7 out times x to the power 6, because you have to decrease the power by 1 every time you do differentiation. Let's look at the next term. If you have already understood the power rule well by now, you would notice that every time you need to pull the power out whenever you find the f prime, when you pull the power 6 out, it needs to be multiplied to 5, right? So it's kind of like 5 is multiplied to 6, which is 30, times 6 to the power 5, because you need to decrease the power by 1 every time. And what is the next term? The next term is going to be 2. Let's keep it here unchanged. And you see the fact is that when you differentiate x, do you know what is that? It is actually implicit in our power rule, because, for example, if you have a function like x, which is actually power 1, right? So actually, we can apply the power rule to such a problem. F prime is what? You pull the power 1 out. And now x should be power 0, because you need to decrease the power by 1 every time you find a derivative. And obviously, x to the power 0 is 1. So the derivative of this case, f equals x, 1. So I put 1 here, right? And the last bit, the last item is that 7 becomes 0 when you find derivative. So essentially it is done. Or you can write it in a slightly better way. The answer is gonna be something like this. Basically, that's it. And let's do a couple of more examples. So the next one. Let's look at the current one. F of x is equal to square root of x, which is basically the same as x to the power half. And to find the derivative, you can actually apply the power rule again. Although it's not obvious whenever you're given a square root, but what we can do is like this. We can still use the power rule by thinking of n as half. So I pull out the n here. The half is multiplied to x to the power. Now the power should be 1 below half. Like you have to take half minus 1, right? Now, which means you have half times x to the power minus half. And if you are good with exponent manipulation, it's actually the same as half times 1 over x to the power half. Or you can say it's really the same as 1 over 2 times square root of x as the derivative of f, which is square root of x. So let's look at the next problem. So please look at the current function now. We'll try to find the derivative of f. And you don't have that many rules in your mind. You have the term-by-term differentiation, and you understand the power rule well. We don't have that many tricks with us. But please don't make the mistake that if f is 1 over x squared, you may think that we can apply the power rule this way, which is totally false. I didn't say it is allowed. I didn't say it. The power rule can only be applied strictly by looking at a function which looks like x to the power n. Now you have a fraction which is 1 over x squared. I have never said that it is allowed to differentiate 1 over x squared by using the power rule specifically for the denominator. I've never said anything like this. So please follow the rule. And the slightly better way to get around this issue is we have to think of the function f as x to the power minus 2 plus 7 times x to the power minus 3 plus 8 times x minus 10. And now it is safe to say that we can actually use the power rule now. If we use the power rule, we can pull for the first term, we can pull the minus 2 out, x to the power minus 3 plus 7 times minus 3 times x to the power minus 4 plus 8 times 1. Every time you differentiate x, it becomes 1. And minus 0, because constant function, when you do differentiation, is going to be 0. So basically, we can turn it around whenever you see the exponent which is negative. I can write the first term as minus 2 over x cubed, the next term as minus 21 over x to the power 4 plus 8. That's it. That's it. So please look at the current function. Now it is a big fraction, you see? And please, let me emphasize, please don't directly use the power rule like this for a fraction. It doesn't make sense to apply power rule at this moment because you're not seeing the typical form where you can apply the power rule. Now it is actually a fraction. You can call it a quotient. And we'll have more general techniques to deal with such a quotient, maybe a little bit later on. But for now, what you know is term-by-term differentiation and the power rule with you. So to get around this issue, we can actually split the fraction. We split the fraction by looking at 4x squared over x plus 7x over x minus 1 over x. We can split it like this, right? When the denominator has only one term, and we can just split it by keeping the denominator common. And why is it good? Because you see, the first term we can cancel out x as a copy of the common factor x. So it becomes 4x plus 7 minus 1 over x. Because you see the second term here, x is also cancelled. So we have only a constant, 7. And now, to put it in the form where you can apply the power rule, the 1 over x can be reverted to make it look like x to the power minus 1, right? And I think now it is safe that we can find the derivative quite easily by looking at the differentiation problem term by term. 4x becomes 4 times 1, and 7 becomes 0 after applying the differentiation. And the last term is an application of the power rule. Minus, I pull out the power, minus 1 up here, and the power itself becomes minus 2. Because you need to decrease minus 1 by 1. So it's kind of like minus 1 for the exponent of x in the last term. So it's going to be minus 2, right? And it means it's the same as 4 plus x to the power minus 2, which is the same as 4 plus 1 over x squared. So that's the derivative of f prime.